Good evening, everyone. Welcome to the second day session on Applied Accelerated Artificial Intelligence workshop. So today we would be discussing about AI accelerators. And to be very, very specific, we will try to discuss in terms of what we are talking about is GPUs today, right? So the agenda of this particular session of the day would be like this. We'll first start with what are AI accelerators, where are they used, how do they work, one view of the AI accelerators, second view of the AI accelerators, then what are these GPUs, how do you actually think of writing a program in terms of just running it on a CPU as against on multi-core or a parallel program versus a program which you write it on a GPU. Then we'll try to see the architecture or the setup of PARAM Shivay, which is a cluster which also has GPUs, and DGX1. And we will do some demos on these particular systems, okay, very brief small demos to start with, and then we will end up with what would be the benefits of actually working on such a hardware, right? Okay, so if you see, okay, if you see, an AI accelerator is a high performance specialized hardware that is specifically meant for AI workloads, which in turn would be neural networks, machine learning programs, and intensive programs which are basically sensor driven, which involve certain processes which also would link all of this, right? So you can work with a program which has neural networks, which has machine learning, right, which is linked to inputs from some sensor devices. And if you classify it, there are three main types of artificial intelligence accelerators for that matter. You have a CPU, you have a graphics processing unit or a GPU, and then you have field programmable gate arrays or ASICs as well. So these are three actual areas or devices basically wherein you can work with for your AI workloads. And if you see that way, from the classification point of view, you can divide these AI accelerators into two groups based on where actually you can use them, right? So you have these AI accelerators at data centers, and you have these AI accelerators which are on your edge devices, or the devices where you actually do inferencing, which are not very computationally strong devices, right? The devices which are there on the edge. So this is how the classification basically looks like when you talk in terms of where they are placed and how you are going to use them. Now, technically speaking, any of these accelerators, right, are supposed to be working in a co-processor mode. So if you have not worked with it, this is how you actually try to develop a program which could run on an accelerator. You have got two types of programs, right? The programs which are there, which are run on CPU. Then there is some portion, right, of your data, the whole program, which you need to actually transfer to the accelerator. And the accelerator does the processing for you. You get the result again, and then this result is again transferred to your host. Host is nothing but your CPU for that matter. So CPU is a host, your GPU is a device. This is the terminology which generally people use in these type of systems, right? So host is your CPU and the GPU is your device. So when you start writing such programs, what effectively happens is not everything is to be offloaded to a GPU or an accelerator for that matter. The portion which is compute intensive, which is actually required to be run by the GPU, will be required to be offloaded to the GPU, and then it basically is executed and then returned back to the host, which actually does all the other types of work, right? So this is how they are used by people when you start developing your programs and you start writing your programs, right? Now, one view of the AI accelerators, okay, is something like this. You have a CPU, you have a GPU, you have FPGA, and you have VPUs and all. There are various types of accelerators. So from one view of the AI accelerator, what I meant was you actually have a serial and a task parallel workload, okay? And then you have data parallel workloads. So when you have a data parallel workload, it is very good for people to run it on a FPGA and a VPU. Whereas if it's a serial and task parallel workload, these type of workloads are effectively run through the CPU or a GPU. And this all is in a coprocessor mode. So you have PCI Express through which your CPU and the GPU actually communicates. So I hope it's clear that different ways of executing compute intensive workloads by different types of accelerators, right? So this is what is a gist of how you actually can split your workload among these various categories of accelerators. Now, let us try to do a demo and see if we are trying to work on a CPU. Okay, it might be a multi-core CPU, and then you can work on different types of GPUs. So let us try to understand and do a hands-on by these two commands, right, which are written here. CPU related information, if you want to gather, there is something called as LSCPU, which displays the CPU information, and then you have this cat proc CPU info. These two are going to give you the information about the CPU configuration of your system. The snapshots are attached. Similarly, when you see the NVIDIA SMI command, it displays the GPU information. And you have this GPU stat, which gives a better information also, a bit of it. So let us try to do this hands-on and see at 3 different places, okay? So I'll just go to those places and see. Okay, so now I hope this particular command prompt is visible to everyone.
Yes, it is.
Okay, so now this is a GPU system, right? This just a workstation with a GPU. Okay, so we'll try to do 2 things now. First, we'll try to understand what type of CPU this has got. Okay, so if you see this LSCPU, the architecture is informed. We have what type of operational modes this CPU can work on, what type of endianism is there, okay, how many types of how many CPU cores are there in this, okay, and then what is the megahertz speed of a CPU, what is the maximum speed, what is the minimum speed, okay, and the model, and how many threads per core, so hyper threading concept there, and how many cores per socket. So this is a general thing about this particular system, right? Now let us try to understand what type of GPU this has got. If you see this particular system has a Quadro K5200 GPU. So this tells about the GPU number, okay, the name, and all of this, like fan speed, then compute node, the index, okay, all of this. So this you can go through in detail when that afterwards, but you get the information about this particular GPU. Now let us try to go to another place now, which is our DGX. Okay, so let us try to do the same thing again. So if you go to the DGX, so this DGX has got 80 cores, 80 CPU cores. That's what it means, right? And you have 20 cores per socket. Then you have on node 0 CPU, what are the numbers? 0 to 19, 40 to 59. And node 1 CPUs 20 to 39 and 60 to 79. So this is a DGX server, right? DGX1. So let us try to understand the GPU information about it. Okay, so if you see this, this is a DGX, and if you see the GPUs, you have got GPU 0, GPU 1, GPU 2, 3, 4, and up till 7, and these are all Tesla V100s. Okay, and you have got the memory, the utilization of that memory on that particular GPU. Okay, so this is how the information about your total GPU system, okay, you can gather using NVIDIA SMI. And then for each of these processes, GPUs, which are the processes which are running, okay, and how many, what is the memory which that particular GPU is using, right? All of that information could be gathered from these two commands, right? So LSCPU and NVIDIA SMI. So now let us go to the next slide, which talks about the parallelism, which I had just told, right? I had told about the task parallelism as well as the data parallelism. So let us try to understand it in brief. As to when you talk of data parallelism, the data actually is split into various tasks and given to various tasks. So there is a data decomposition which actually happens too much. And then this is how, like, this block of data goes to this task, this block of data goes to this task, this block of data, the third block goes to the third task, right? And something like this, and then you have this aggregation of all of these results and then do this. This is data parallelism. When you talk task parallelism, let us say you have a small section of data, then you actually split, okay, that particular data, which can be unique for each of the tasks. And then it's not necessary that here the tasks will use the same data or these tasks will do the same work. Okay, so basically it is the decomposition at what level? Decomposition at the task level, decomposition at the data level, right? So here these are different tasks, you get the same data, or you get different data for the same type of task, right? So this is how actually is a basic difference between the task and data parallelism. And from the second view of AI accelerators, what I meant was, you can use these accelerators. If you see here, it starts with CPU, GPU, TPU, and then all the way up till quantum accelerators. So the idea here is that all of these different levels of complexities which are available in these accelerators could be used as different levels of your programming applications, right? So you actually can use with these your sensors, you can do data conditioning, you can develop in your algorithms, you can do actually human in loop and all of that, human machine interaction at various levels, various complexities. The same hardware could be used, right? And then you can have application development for various users. Then you talk about explainable AI, you can talk about matrices, you can talk about verification, validation, policy, ethics, safety training. So it actually is a very, very huge gamut of applications, course of action requirements, and then the application or the area where you are working in, and the hardware. So these are all linked, right? And this is what I thought like we would cover it as a second view of an AI accelerator, right? Two views of AI accelerator. One from the view of how you are going to do computations only, computational workload, and the second thing is how can it be used for other things, right? Like inferencing or data conditioning or something, processing a structured data or unstructured data. Of course they are all considered as data workloads, but the idea was at different places you want different type of accelerators and different type of usage for those accelerators, right? So that was the intention of this specific slide. Okay, so now let us try to understand the difference between the CPU and the GPU, which is something like this. It's basically having multiple cores, the CPU, and you have L1 cache for each of the core, then you have controls unit for each of these cores, and then you have got L2 cache, L3 cache, and RAM. For GPU, you have got these huge, massively parallel processing cores with you. And each of these, okay, have got their own control and cache. And then you have L2 cache, you have the RAM. The way in which these are used for massively parallel applications, okay, the way in which they are programmed are a bit different. Uh, then yeah, that is how basically it is done. Not going into the details of them, but this is how the difference lies in the CPU architecture and the GPU architecture. So massively parallel programming is supported by GPUs. And this is an example which I thought this slide shows. If there is a GPU, right, for the data center, and then the same type or the similar family of GPUs, okay, for the edge. So the idea was the difference is in this design of how many cores you're working with, right? How is the connectivity between the CPU and the GPU stuff, because this is totally a embedded type of a Jackson Xavier NX processor engine, which also has a high-speed IO and memory fabric. So this is for the edge devices, wherein when we would be doing inferencing, we will try to show you how to use such devices for doing your inferencing portion of your problem which you are trying to solve, right? And this is the GPU for data center. You have B100s, you have A100s, right? And so many of them which are to be used by data centers for training your models, right? Coming up with a lot of different type of approaches for models. Then you have basically so many other things which you can do on these GPUs, which are basically for the data center, right? And you have this NVLink stuff and all of that. So this is the difference in the architecture and the design of these accelerators at the data center level and at the edge level. Okay, so now let us try to understand a very, very basic thing of something which is called as sequential reduction. For example, you have to add these numbers together. So let us say, how does a sequential processing happen for it? It is something like you go on adding 13 plus 27, then you get that, and then you add 15 to it, then to 14, then 33, to 24 and 6. So this is a way in which a sequential processing happens. So if you see this particular type of reduction operation, you will see that you cannot do anything in parallel. It cannot be done parallelly, right? Because this particular thing depends on the sum of this and so on and so forth. So this is basically a way in which a CPU actually works for you. When you come down to a parallel reduction, okay, so the idea is something like this. You can do this particular addition, okay, at one particular core or one particular CPU or a processing element, and then you can do this on a different processing element, and so on and so forth, and then you can go on summing it up, right? So this is a way of parallel reduction. Now, how do you do this parallel reduction using a GPU? So the idea is, we are trying to assume that you have got, let us say, n number of elements. So you basically start with n by 2 threads. So you use one thread for every 2 elements. Each thread computes the sum of the corresponding elements which you are using it for, and then you store the result, okay, in one of the threads. So iteratively at each step, the number of thread is going to be halved, okay, and the step size, right, between the corresponding elements will go on doubling, and ultimately you get the sum uh, as a sum of an array of all of this, and then you get the result. So this is how actually you actually move from a sequential type of a execution thinking to parallel, and then to the concept of GPUs with many threads. Okay, so now this is actually a snapshot which shows about the difference in the processing time for a small classification problem, okay, uh, which we ran on the GPU as against the CPU. So here, if you see, for epochs ranging from 1 to 99, okay, you see the time taken for each epoch on a CPU as against on a GPU, right? So you can see that you have got, for if there is only one epoch to be run, you get about 154.26 seconds time to get executed on a CPU, as against 18.21 seconds on a GPU, right? This was just to show you the time difference, right, between something which you run on a CPU and something which you run on a GPU, okay, all the way up till 100 epochs. So the idea was to just show you the difference, then show you the difference, and then you can assume that just for a very, very small classification problem, right, of some diabetic retinopathy detection, just we tried doing it for some application, okay, and this was just a idea to be given, so that the time difference for execution it on a CPU and a GPU, okay. So now, if you are trying to train a convolutional neural network on multiple GPUs with TensorFlow, right, this is how it's going to happen. You have your CPU, right, and CPU has to be the master, and then you have these co-processors which are your GPUs. So actually what is happening when you try to develop a convolutional neural network, or for that matter neural network, you will have gradients, losses, weights, and all of this, right? And then you will have your own model, right, which basically would be running on a GPU. So you have these variables, you have to calculate the mean, the updation of all of this, and then it has to be again fed back to your model for improving its accuracy and so on and so forth. So the idea is this is how it's going to be linked. So CPU does certain specific portion which is not actually effectively to be done by a GPU, because GPU is compute hungry type of a processing element, right? You have to give it a lot of computations. You cannot depend on this data intensive or IO intensive applications to be effectively run on GPU. So that is one thing which you should keep in mind, that not all applications are suited to be running on a GPU. They have to be massively parallel requirement should be there for that type of application. Then only it actually gives you the benefit and the advantage of trying to solve a problem on a GPU. So this is how it's going to actually be used when you are trying to go ahead in these classes, because you will be working on various types of models, how do you accelerate them and all of that. So this is the basic idea of what is going to come. This is example of a multi GPU type of a setup. You can have a single GPU type of a setup, and then you can have a cluster GPU with clusters, right? That type of a setup. So let us try to see in the days to come as to how we can use this type of a setup also for solving certain problems. Okay, so this is the PARAM Shivay cluster at IIT Varanasi. This gives you about 837 teraflops. If you see the configuration of this system, right, you have got about 4 login nodes, you have 192 compute nodes, and then you have GPU nodes with NVIDIA Tesla V100. So the same V100 which I showed you on the DGX. So DGX has got a very specific type of a setup which I will show you in the next slide. But the idea here is, here also we are using V100s. There are 11 numbers, and then you have actually InfiniBand switch, and then the communication. Then you have primary storage of about 750 terabytes and 250 terabytes of archival storage. Then you have got high memory compute nodes, right? So there are about 20 nodes, 800 cores. All of this information is available on the NSM website. The reference is also given. So if you see the GPU compute node specifications here, you have got about 11 nodes with 440 CPU cores, and then you have got about 2 into V100 PCI accelerated cards, each with 5120 CUDA cores, right? So this is basically with each node which you're talking of. So this is the total design of your PARAM Shivay cluster which you have. And then this is the DGX1 cluster, DGX1 server actually. So if you see this architecture, this is something which is having a NVLink, right? So NVLink is a proprietary bus link, okay, which is specifically developed by NVIDIA, and it uses its NVLink in its servers, right? So if you see here, you have got about 8 GPU cards, right? And then you have PCI switches, then you have your CPU cores, then you have NIC. So if you see this DGX1 server, you have got 8 Tesla V100s, you have got 256 GB of memory, you have got dual 20-core Intel Xeon CPU processors, and then you have got about 40,960 CUDA cores, you have got 5,120 tensor cores, you have these system memory and the network, right? So this is the architecture of your DGX1. Now let us try to go and see what is one of the very important features for these V100 GPUs. One of the very, very important things which is there is a tensor core. So there is an animation which is also running on the slide, which tells you about how basically these tensor cores can process, right, floating point operations. So FP16 or FP32 or FP4, sorry, int4 and all, so on and so forth. So the idea here is you perform an operation of the type A into B plus C, which is equal to D. So you are trying to actually do a matrix processing, okay, using arrays. And then it is something like a accumulation which you are trying to do in the end, right? So this is a generic representation of this, and then you can work with any type of values. It can be FP16 or FP32, and you can get the result in one of the various things, okay? So now, why is a tensor core very, very important? So if you see one arithmetic operation that holds very, very high importance is a matrix multiplication. So you tend to solve a lot of your problems using matrix multiplications. And if you specifically see matrix multiplication of, let us say, a 4 cross 4 matrix, it involves about 64 multiplications and 48 additions. So this is where this tensor core is going to be of help to us. So the whole GPU is made up of two types of cores. One is the CUDA core and another one is the tensor core. So notionally, if you see, CUDA cores would be a bit slower, but they will give you a lot of significant precision. Whereas a tensor core, right, is very, very fast, and along the compensating for this speed, right, you lose some precision, okay? So all tensor core basically does is that it accelerates the speed of your matrix multiplication. So tensor cores are able to multiply two FP16 matrices 4 into 4 and add the multiplicative product, right, and then to the accumulator. So this is general matrix multiplication, or GEM. One of the things is, instead of needing to use many CUDA cores and more clocks to accomplish a task, let us say, it can be done in a single clock cycle with lot of dramatic speed up for applications which involve machine learning, this, that, everything, okay, on these tensor cores. So this is how we can think of actually trying to create, okay, easy to understand representations of whatever we would be using in our deep learning or machine learning type of model development. You can show it as equivalent matrix multiplications for forward propagation or your activation gradient calculation, and then weight gradient calculation when you're trying to do it for a fully connected layer in the end. So you can see here that these are the matrices, right, size of the matrix, and then you have these output activations, input activation, weights, and all of that put in a manner which could be easily, right, executed by tensor cores. So if you see that way, how basically people could use tensor cores is that you can use tensor cores in CUDA libraries. You have this cuClass, which uses tensor core to speed up the gem computations, and then CUDNN also uses tensor cores to speed up both the convolutions and the recurrent neural networks, or RNNs. So this is how you could specifically start using tensor cores for your own application development, right? And then there is something which is called as CUDA wrap matrix multiply accumulate, or WMMA. This will help you to actually use tensor cores very fast. And then how these tensor cores could be used for various other applications, right? So here there is something which is an application of a sampling thing, right? So you have something called as a deep learning super sampler. So what effectively people have tried to do is that you render a frame at a very low resolution, right? And then once it is finished, right, you increase the resolution so that it matches with your screen dimensions of the monitor. That way you get the performance benefit of processing fewer pixels, but still get a very nice looking image on the screen, right? So this is actually how tensor cores are being used. Okay, so now there is a demo which we thought we will show you of a matrix operation, right, on a hardware which has tensor cores, and I will like to show it to you, and this is how the result will look like. If you see this, we are trying to use 3 matrices, 4096 cross 4096 each. And then you do the computation, which is the same thing which we were thinking of. D is equal to A into B plus C. And we have done that on GPU without tensor cores, without tensor cores and with tensor cores. So let me just take you to that this thing, and then I will just execute and discuss that program as well in brief. So let me just 1 minute. Give me a sec. Yeah. Okay. So
Can you increase the font size?
1 minute. I'll do that.
Yes, this is good. This is good.
Okay, sure. So
You can explain what you have fired and what's happening.
yes, I'll explain the program as well. The idea is that we are trying to compute, okay, D is equal to A into B plus C, with tensor core and without tensor cores, right? So let me just show the program once. There are 3 programs actually. So the yes, so this is a sample program which talks of trying to use something which is called as WMMA. So this actually means wrap, matrix, multiply, and accumulate. So the idea here is you are trying to use these matrix tile dimensions, and then this is a 1 minute. Okay. Okay. Yeah. So this is actually WMMA initialization. Then you work with tensor cores using WMMA F16 tensor core uh, type of thing instead of just CUDA cores. I will show you a GPU program also. There is a GPU program also which does not use this tensor core, right? Of course, you use your block ID, block dimension, thread ID, which gives you all of these, right? The same thing. But here you are trying to work with warps, right? And that is why it's called as warp MMA. And here it is basically trying to understand a very, very basic same thing which you try to do, but you are using the CUDA tensor thing here, right? So which I just now showed you. So I'll show you a GPU program also. I'm not going into the details, but it's a CUDA program. So if you can understand CUDA programming, you'll understand. But here the idea is to have this particular thing used, okay, which is a additional thing which has been now added into your CUDA thing, okay. So this everywhere uses this tensor core, and then you can run it using this same grid dimension, block dimension type of stuff, okay, and then you synchronize it and then you do things. So this is how it is. And then this is a GPU program without the tensor core, wherein you just do CUDA matrix addition, use the same block IDX, block dimension, and then come up with this. Then you do the same thing, and then you run this using the grid dimension, block dimension type of thing. And then this is again a very, very basic rudimentary CPU version, which talks of doing the same thing and then trying to do the multiplication and then stuff like that. So yeah, so this is just trying to also use the unified memory. And yeah, so that's it. So I thought like this is just a idea of how basically people could use tensor cores and how they can use GPU cores, okay, sorry, CUDA cores for that matter. And this was just a idea of doing things. And then this was the idea of trying to tell the thing that people can start programming using the tensor cores, and then we can actually see certain other things on the DGX, and we can do all of those things as we go ahead in the days to come. We'll try to actually execute a lot of programs, and then from the benefits point of view, right, sustainability is one thing, the speed is another thing, scalability, heterogeneous architecture you could utilize, then the overall efficiency, right, improves. So these are certain specific benefits of trying to go in for GPU programming. And then yes, so we can actually see some more things in 1 minute. Let me, so okay, so this is a thing which I had left actually, so I thought I'll share that with you. So if you see the GPU stat again gives you which GPU you are going to use, right? Tesla V100, 32 GB of memory, then the temperature at which it is working, and then how much percentage it is being utilized with, what are the various programs which are running, how much of it is being utilized, how much memory is being utilized by which program. So this is a way of trying to actually see it in a different format instead of trying to use NVIDIA SMI. So these are certain things which you can go on trying and then do things.